Hello, everybody. Welcome back. How's the homework going? 3A, you already did. And I didn't mean for that to be there. I meant to have, because it's a problem from the previous homework. And in the previous homework, you did find the long run percentage of no green bugs on the grid. And I meant for this to be 3 different questions, not that question repeated, and 2 others. So you don't have to do A. So 3 is the bug problem. And let me give you the matrix either to remind you of what you did in the previous assignment or just to get it right. So we're all working from the same matrix. So in 3, the matrix is 0, 1, 2, 3, 0, 1, 2, 3, 1/2, 1/2, 0, 0, 1/6, 1/2, 1/3, 0, 0, 1/3, 1/2, 1/6, 0, 0, 1/2, 1/2. Okay, and so xn is the number of green bugs on the grid at time n. Initially, the red bug is at node 1, and there is 1 green bug located at node 2. Compute the expected number of moves until the red bug first eats a green bug. The nodes are unimportant, the numbers of the nodes, because the red bug just randomly selects from one of the other nodes. So he doesn't care that he started on node 1 or that he's jumping to node 2 or whatever it is I just said. So I'm going to let T be the time to eat a green bug. I want to find the expected time to eat a green bug, given that, again, the nodes are not important. So I want the expected time that a green bug is eaten, given we're starting with 1 green bug on the grid. And this is going to be a first step type analysis. It's going to be a first step analysis, but it's not exactly one of those questions. But I do want this expected value. And just like the other first step analyses, I'm going to define it at different starting points. So UI, I'm going to define that to be the expected time to eat a green bug, given that we start with I green bugs on the grid. And so I want U1. So far, pretty similar. And again, the numbers of the nodes that the bugs are on are really irrelevant because the red bug is equally likely to jump anywhere. So note that we can say, starting with 3 green bugs on the grid, that means we have 1 red and 3 green, so all nodes are occupied. So we will definitely have a bug eaten in 1 time step. That red bug is going to jump, definitely going to eat. So a green eaten on the first time step. Okay, so let's go back to starting with 1 green bug, which is what I care about. We'll start with 1 green. And I want to find U1, or at least an expression for U1. So we're going to have to take at least 1 time step for any bugs to be eaten. So there's a 1 plus, like the system has to move. And then with probability 1/3, I'm going to label this down here. With probability 1/3, the red bug will happen to jump exactly to that node of the green bug. So the red bug eats the green, and it is over. And that means we count 0 more steps. Again, this is a first step analysis, and you can think about it the same way we've done it, but it's not like one we've actually done. And then with probability 2/3, that means the red bug jumps to an empty node. And then we have to figure out what happens from there. So with probability 1/2, after the jump, we make a decision about whether a green bug joins. With probability 1/2, no additional green joins. And then we just want to count the number of time steps starting with 1 green bug. So we have the initial jump, and then this is us starting over, assuming no extra green bugs join the grid, and also assuming that the red bug didn't catch the green bug. And then with probability 1/2, we want to figure out how many time steps it takes for the red bug to catch a green bug when they start with 2 on the grid, because with probability 1/2, another green bug joined the grid. And so now we have a red and 2 greens and are starting over. So let me erase some of this. You can see the labels a little better. This 1/2 is a new green joins. There are two unknowns here. And remember, U3 is already known. So I think I'll leave it to you guys to find an expression for U2. We start with, these are my grids, and I don't know if you could see this red on the blackboard. There it is. Start with one red and one green. So we want the time until the red bug first eats a green bug. So the first move of the next time step is the red bug jumps. So that's one time step. And then with probability 1/3, 1 out of 1, 2, 3, the red bug eats the green bug and the game is over. So we count 0 more time steps. To find this thing that I'm circling in yellow, I want a condition on the event that happens at the first time step, but I don't actually want a condition on X1, the number of bugs after one time step, because as Sage was saying, I don't know then if we still have that original one bug or if he got eaten and another one joined, and that's why there's one bug. You'd be conditioning on whether or not the red bug ate at time 1. And so that's sort of its own probability, like it eats with probability 1/3 or 2/3 is not gotten from the transition matrix or the Markov process, unfortunately. But I could write this out all formally where I would break it up into 2 parts. And then after the conditional line, I would say the red bug eats in the next step. And then times the probability the red bug eats. And I don't know. I guess I kind of don't want to write that all down right now. There are just 2 here. I mean, there's a third U. There's a U3. Oh, wait. There's no U0. There is one, but I don't care about it. Because it didn't come up in these systems of equations that we wrote. So U3 was 1. U1 comes up in an equation where it's written in terms of U1 and U2. And then I'm asking you guys to write out the equation for U2, which won't involve, it'll be an equation of U1 and U2. So you'll have 2 equations and 2 unknowns, the U1 and the U2. U0, if we start with 0 green bugs and want to compute the expected number of time steps until the red bug eats a green bug, we're going to have to take at least 1. And then we're going to have to condition on whether a green bug joined and what happened after that. Okay, I did want to mention something about problem 2. It's quite fast, and I wanted to draw your attention to theorem pi 2. So for problem 2, use, and I'll remind you of what this is, theorem pi 2. And this says if you have an irreducible Markov chain, a stationary distribution exists if and only if the chain is positive recurrent. And in this case, it is unique and given by 1 over the expected time to return to a state I, starting from state I. So in this case, it is unique, and pi I is 1 over the expected time starting from I to first return to state I. So I stated this in class, and I proved one part of one piece of it so far in the notes. We want, in this problem, we're starting with D balls in the second box. So you could call the second box the first box, or you can just say I'm starting with 0 in the first box. So we want, so if xn is the number in the first box, let me remind you, because I will put these solutions out today, but another thing I haven't put out yet is we found the stationary distribution in homework 3. So pi sub I, the probability that there's I balls in the first box or urn, is D choose I, 2 to the D. So we want, starting from all balls in box 2, so that's 0 in box 1, we want the expected time to return to 0 in box 1. And now, from that point on, it truly is a one-liner. I know I say that, and sometimes you're like, it took me 2 or 3, I did it wrong. And that was just me being ambitious. But there's truly only one more step here. My pi I was incorrect. Let me get a correction color. This was 1/2 to the D. Okay. Guess I have time for maybe one more. Okay. One quick hint on the grad problem, problem 6B. You want to find an expression for the expected value of t. So xn is a sequence of independent and identically distributed random variables from some distribution, and then you have this yn, which is the max process. So you've got this yn, which is the max of x1 through xn. And in part A, you would have found a probability transition matrix. And for part B, I would condition on whether or not, so this chain is going to stop the first time this maximum exceeds the number m. So I would stop, yeah, it is just a graph problem. So I would stop this chain if that happened. So condition on whether or not the first y, let me say y1, which is also x1, so you can condition on x1. Condition on whether or not y1 is less than m or greater than or equal to m. That's the first step, which will turn, oh gosh, no, it isn't a grad problem. I left off the grad problem though. Okay. It's right now I want to put a poll up, but I have to make these Zoom polls before the class. It doesn't help. All right, it's a grad problem. Do it. Thanks, Graham. You are everyone's hero right now. So number 6 is a grad problem, but this would be the first step I would take. Condition on whether or not y1 or equivalently x1, because x1 is the same as y1, is less than m or greater than or equal to m, and then try to simplify some of those pieces. And let me do one of them. So what's the expected value of t given that y1 is less than m? So t is going to be the first time we see the y process greater than m. So if y1 is less than m, then we take one step because it didn't happen. And then we want the expected value of t all over again. Like we're starting over. So, all right, you guys didn't even ask. All right, so let's do something new. I was rushing the simulation last time. It's the most basic kind of simulation you can do, but basically you need to grab a uniform 0, 1 number from any software you want. And if you look at the notes that I posted last time, I gave commands for several different, I don't get it, but I'll move on. I gave the command to do this for several different languages, including R, which is what I'm suggesting for someone who knows no languages. And then let's see, in part, let's talk about B, 5B. This is not me continuing to waste all the time doing the homework. This is a continuation of our last class discussion. We want to find the limiting distribution for this chain. So it has a transition matrix, 1/4, 3/4, and 2/5, 3/5. And in part B, we want to simulate many sample paths of this chain starting from state 0 forward for a long time. So you don't have to graph this, but let's envision 0 and 1. And we're going to start here every single run of this chain. So then you look at time step 1, time step 2, time step 3. For each of these time steps, you grab yourself a uniform 0, 1 random variable from the random number generator from whatever software you're using. And then you look at the matrix to figure out where to go. Because I'm currently at state 0, I want to look at the 0 row of the matrix. And that says with probability 1/4, go back to state 0, with probability 3/4, move to state 1. So we talked last time a little bit about breaking up the unit interval into an interval of length 1/4 and 3/4. You can break it up in weirder ways, but so if your uniform falls in here, then you want to assign the value 0 for the chain at time 1. And if your uniform falls in here, then you want to assign the value 1 for the chain at time 1. So let's say this uniform was 0.7, then looking at the circled row of the matrix, that tells you that you're moving to state 1. Now from state 1, you grab a new uniform associated with time step 2, and because you're starting at state 1, you look at the second row of the matrix and decide with that second uniform whether you're moving back to 0 or staying at 1. And so the point of this was to go for a long time, and a long time is up to you. Personally, I would go until I didn't see much change in the limiting distributions. It's going to be really quick for this particular Markov chain, but let's just say go 100 time steps. For some Markov chain, it's going to take millions. This one will probably take 3. Let's just be safe and go with 100 time steps. So you go out to time 100 or whatever it is that you picked, and you will end up here sometimes and here sometimes, and then return the proportion of time you found yourself at state 0 and the proportion of time you found yourself at state 1 over several trials. I'm just going to throw a number out there, 100,000 trials. Because it's so fast and easy, I would just do a lot. And then they should match the proportions you got in part A of the problem. Yes, there's going to be practice problems posted Thursday or Friday at the latest, and then solutions over the weekend. And next Monday, we'll have a regular class, but next Wednesday will be all devoted to review. And I'll also have an extra like evening review outside of class to be announced. Okay, does that simulation make sense? As much as, if you're brand new, I bet it's still confusing, but okay, we're gonna do something new then. So we're starting, not gonna get very far, but we're starting into continuous time. This is a whole new section of the course. And really, if you've been lost on anything, you can sort of start over here. Continuous time, Markov processes. I talked on the very first day of class about the fact that we use process to talk about continuous time. And yet it's still just kind of natural to call it a Markov chain. So it wouldn't be wrong to call it a chain. And in fact, people say processes, but they always write CTMC for continuous time Markov chain. I've never seen anyone abbreviate CTMP. So this stands for continuous time Markov chain. So we're still in a discrete state space. You might want to write that, but I'm too lazy to write it. Still in a discrete state space. So what's going to happen here is we're going to have a discrete state space, which doesn't have to be integer valued, nor does it have to be positive integers. I'm going to draw something that is positive integers. And we're going to have events moving us at certain continuous time points. I'm going to erase this so I can move this over. I need a little more space. So imagine this is time and it is continuously measured time. And these are a number of customers in some store that you are lurking out in the bushes by the door, being a total creep. You get there early and there's no one in the store. And you look, starting at time 0 is the time they open, and you wait for customers to arrive. So I'm going to make a simplified model of what I just said. Let's just say one customer arrives at a time, or we count groups, like if 5 come at a time. I don't want to deal with that right now. So at time 1, that doesn't make any sense because there could be 100 people in there by time 1, or no one has come in, or something in between. So we're going to have some sort of model of an amount of time, a continuous random variable that will go by until someone comes in the store. And so the arrival times, what I'm showing you are arrival times, and they're not equally spaced. And these are continuous random variables, like a T1 and a T2 and a T3. And these are actually going to come from the exponential distribution, which I'm going to review today. So the TIs are going to be independent and identically distributed from the exponential distribution with rate lambda. If you read that chapter 1 notes that I put out, you already know this notation, but if not, it's okay. We're going to talk about it today. And we use the exponential distribution a lot in Markov chains because it has a lack of memory property that you may have heard of, but if not, we're going to do it. And this is going to allow us to say where we're going depends only on where we are and not how long we were where we were and stuff like that. So this process is going to run like this. If we start at 0, there's going to be some random time where we'll jump up by 1 and some random time where we'll jump up by 1. And in between, there's other random times, you know, where we go down. But the X's I've drawn are where we jump up by 1. So prime example of a discrete state space, but continuous time. So I don't know if you all got my announcement because apparently not everyone sees those, but we're about to go into a review mode that will be quite basic. And I invite you to leave if you know all this stuff. I don't want to, not that you're not always free, but this is going to be incredibly boring, I think. Okay, so let's talk about the exponential distribution. So I'm going to forget time right now and just go back to like X's for our random variables. So here goes, the exponential distribution. So this is a continuous random variable. I'm going to call it X. And recall from some probability you've had before that the probability that X for a continuous random variable is equal to any particular value is always 0. You know, the idea is there's just too many values. So if instead of this, we are going to measure the height of the next person we run into, socially distanced from, but see, the probability that they're between 3 feet and 7 feet is quite large, almost 1. But the probability they're between 62 inches and 64 inches is smaller, 62, 63 even smaller, 62, 62.5 smaller. And you get it, as it's shrinking, the probability is going to go to 0 because there's just a continuum, too many possibilities. So for all continuous random variables, this is true. So we talk about a probability density function, or PDF. And this is going to be a curve under which area represents probability. And I could draw a generic one now and talk about probabilities, but I won't. I'm just going to go back to the exponential distribution. So I guess I don't have to write this. I'm still under my subtitle of exponential distribution, although I just wrote 2 things that were pretty generic out. So I'm going to let lambda greater than 0 be a fixed number, which is a parameter for this distribution. And there's 2 ways people write the exponential distribution. So the PDF probability density function, I'm going to call f of x, or maybe you want to put the lambda in there, f of x and lambda. And I usually use a semicolon between them. It's not really going to come up in this class very much, but I usually use a semicolon to distinguish between the variables in case we have a joint distribution with several variables, and the parameters, also in case we have several parameters, as opposed to just a comma. Some people use a line there. I think that's a loaded statement about conditional probability and being Bayesian, but it's also okay. So the PDF, one way to write it is lambda e to the minus lambda x on x greater than 0 or greater than or equal to 0. The area under the curve over any single point is 0. So it really doesn't matter where that goes. And 0 otherwise. And if you've read my intro chapter 1, you'll see that I like to write these with indicator functions. You do not have to do this, and it's not going to come up very much in this course like it does if you take, say, mathematical statistics with me. But I can write this with this function I on 0 to infinity of x. And this is a function that takes on the value 1 if x is in that interval. So this indicator function is going to be 0 otherwise. So it's just a compact way of me writing down these two cases up here. Okay, so this is what I mean when I talk about an exponential distribution that looks like this. So if we plot it as a function of x, it starts at lambda and then it goes down, oh, faster than that, it goes down exponentially. Probably faster than that as well. I'm just not trying this very well. Exponential things go down fast. And you might have written your exponential PDF down another way, and I'll talk about that in a second. But if we want, say, the probability that x is between two numbers a and b, where a and b are, a is smaller than b, then you would just look at these two lines and integrate and find that area. So this would be the integral from a to b of f of x dx. Okay, so in the way I've parameterized my exponential distribution, lambda is called a rate parameter. So I call it a rate parameter here, and it's used as a random variable to model rates of occurrences of things. So as I was saying before with the customers of the store, in the store, if people are arriving at a rate of lambda per hour, I mean, that's something we're going to be talking about a lot. And the mean of this distribution, the mean or expected value, as you know, don't worry, I'm not going to drag you through it. It's going to be the integral over the whole space of x times the PDF. This is the integral over the whole space of x times lambda e to the minus lambda x dx. By the way, there may be a small cheat sheet by me, not a home cheat sheet, that you will have during the exam. So when I distribute the review problems, I will also distribute that so you'll know exactly what you have. You can do integration by parts on this. I would do something different. I don't really want to talk about it right now, but this is 1 over lambda. So if x is the time, the inter-arrival time of a customer, and if we define, say, if people arrive, so suppose they arrive at a rate of 2 per hour, then you're going out of business, then the expected time between arrivals we just computed is going to be 1 over lambda, in this case 1 over 2. So if I use 2 to denote a rate parameter, then 1 over 2 is actually the expected number of arrivals. And some people parameterize their exponential distribution so that lambda is actually not the rate, but the mean. And there's this inverse relationship. So if you have this PDF, and I'm really only going to use this one, but I'll write them both down and you can use another one. The PDF that I just described here, I'm going to denote this by saying x is exponential with rate equals lambda. Now, people usually don't put that rate word in there, but if they don't, you're not sure which exponential they're talking about. And if the PDF is supposed to be 1 over lambda e to the minus x over lambda, if you redid everything, the expected value there would be lambda. So now lambda is the mean of the distribution. And I won't be using this, so you don't really have to worry about it. But I would call this an exponential distribution with mean lambda. The point of this conversation is most people just write exponential lambda, and then you're not sure if you're reading a book or a journal article. You really have to back up and figure out what they mean by that. So that's why I add these words. And I will probably never even use this one. And then we can show that the expected value of x, which is the integral from 0 to infinity of x times lambda e to the minus lambda x dx, we can show that this is 1 over lambda. And so this is the mean, and it's 1 over the rate, and there's this 1 over relationship. And we also can show that the variance of x, which is the expected value of x minus its mean squared, where mu is this expectation for x, There's a more computationally pleasing version of the formula for variance. It's the expected value of x squared plus the expected value of x all squared. Please check out chapter 1 where I wrote some of this in detail. And also I'd be happy to go much slower in an office hour or another appointment. But if you go through this, you'll actually get 1 over lambda squared. And so when I write this, you should know that this is the PDF and this is the mean and this is the variance, and those are things I will include on the exam cheat sheet. And this is the last thing that will make it onto the exam. That's not true. Friday. Maybe this is. I don't know. I'll tell you this week. It's either today or Friday. Okay. Great. So I wanted to review other distributions that we're going to need, but since I have very little time left, let me talk about a very important property of the exponential distribution, and that is called the lack of memory or memoryless property. So suppose that X has an exponential distribution with rate lambda, then for any S and T greater than or equal to 0, so those are just fixed numbers, the probability that X is greater than S plus T, given that X is greater than S, is the probability that X is greater than T. So what this is saying is, suppose that X is a time, an inter-arrival or inter-event time in Markov chains where you're waiting for something to happen. So you're sitting in the bushes outside of that store and you're waiting for the next customer to come in. And suppose that model is in between customers, there's an exponential amount of time with some rate lambda. This is saying that given that you've waited at least S units of time, the probability that you have to wait at least T more is just the probability you have to wait at least T units of time. So we're going to prove this, but essentially what this means for us is you are sitting in the bushes, right? And you get there when they open the store and you're watching people come in and you are recording the inter-arrival times. And then you get distracted because like a cop approaches you. It says, what are you doing in the bushes? And you explain that you're doing a project for your Markov chains class. And then you go back to looking. And when you go back, how much time do you have to wait for the next person to arrive to the store? It's still exponential with rate lambda. The fact that you lost some time doesn't matter. The fact that some time went by really doesn't matter. And that's going to be really important for us to talk about a Markov property in the continuous time setting, because where you go should depend on where you are, not how long you were there. So please come back. And yeah, I guess it is my office hour in 3, 2, 1.